Everyone feel refreshed after 10 minutes of doing something else?
I had to walk around and stretch.
Yeah. Go do some shuffle dance or go do the Wednesday dance.
Do the Wednesday.
Go do the Wednesday.
This grown man. I just see this grown man doing the Wednesday dance.
That's such a great scene. Oh my gosh.
Yeah, that's pretty funny.
I can't even believe I've watched professional dancers do it underwater on skates and all over the place. Everyone's doing it. It's so funny. All right, well, let's go ahead and continue on with our 6-1 section. So the so this is kind of a summary of what we were just talking about. So position is denoted by S of the t value. And again, we are moving just on a line. And velocity is the derivative of position. Displacement is the definite integral of velocity. And then distance traveled is the definite integral of speed. And so now our next goal is to find position from velocity. And there are two ways to do this. And the way that they show here, this is called the future value method or the fundamental theorem of calculus method. And then there's going to be a second method called the antiderivative method. This is the method I would recommend using just because it generalizes to other topics other than just position and velocity. So it generalizes to formulas that you'll see in economics and biology and things like that. So this would be the recommendation. Now, one thing I want to point out is that in here, we have an X. And that X is a dummy variable, which means it's not really a variable. What do I mean by that? Let's go back to Calc 1 for a second. So if we are integrating something like x cubed dx on the interval 0 to 1, that expression has no variable. That is actually just a constant, and that x is acting like a placeholder. That x is not really a variable because look what happens. We do our integration, we evaluate on our interval, we plug in our limits of integration, and we get that this expression here is really just the constant 1/4. So it's just a placeholder. That x is not a variable. It's called a dummy variable because it looks like a variable, but it's not really a variable. It's just a placeholder until we finish the integration. And so up here, notice that there is a t up in the upper limit of integration there. That means that we're going to end up with a function. That is not just a dummy variable placeholder. So for example, let's come back to pen. So for example, if we integrate 0 to t x squared dx, this is going to end up being a function of t. So we integrate using our power rule. We plug in our upper and lower limit. So we'll get t cubed over 3 minus 0. And so notice that we get a function of t. This over here is just a constant. The thing that's common for both of these is that we end up with no x's. So in both cases, x is a dummy variable. It's just a placeholder. So don't be fooled. This is not what we normally think of as a variable. T is a variable, right? We end up with a function of t. So that is the independent variable for that expression. Oh, shoot. Did it do it again? Why is it doing that to me? All right, so it seems like I trigger the eraser and then it goes back. Okay, I just got to get efficient. All right, so let's try a couple of these. So here we start with a velocity function and they ask us some questions. They say, determine when the motion is in the positive direction, when it's in the negative direction, find the displacement and find the distance traveled. So first and foremost, we are going to, we want to graph this velocity function because it's a lot easier to notice where it's moving in the positive direction and negative direction if we have a graph. It's much, much easier. So let's go ahead and do that. Now this is a quadratic and we know that its graph is going to be a parabola opening up, and pretty easy to factor that velocity function. And if we set this velocity function equal to 0, we notice that the zeros are 0 and 2. Any question on that? Whoops. To try to move this guy out. It's not liking that. Let's see, what do I have to do first? Maybe I can just grab it. Nope, it wants that to be a pen no matter what. Oh, I know what I can do. I can use my mouse, right? There, let's just move it like that. Okay, that's better. All right, any questions on how, let's see, where is delete? There. So those are going to be the zeros of the velocity function. And we already know that it's a parabola opening up. And so we know the vertex is going to be right in between those two. And we're not trying to get fancy here. We're just drawing a rough sketch. So we know that, okay, there's a 0 there. There's a 0 there. This interval is stopping at 3. We know it's a parabola opening up. And so we don't even need to find anything more. We're just trying to get a sense of what the behavior is. So there we have it. Okay. So that tells us then, so part A tells us that we are moving in the negative direction when the velocity is below the t-axis. So this is v, this is t. So negative is going to be down here, and then positive will be this area up there. So negative direction is going to be on the interval 0 to 2. Positive direction, 2 to 3. Should we use parentheses, brackets, one of one, one of the other? What do y'all think?
I would say a parentheses and a bracket.
That's right. So we are going to look like that. Is everybody clear? At 3, the velocity is not 0. At 3, the velocity is whatever this positive number is here. So it's still moving to the right at that moment because it's not a 0. Now at 2, we definitely can't include 2 because at 2, the particle is not even moving. So it's clearly not moving in a direction. Okay, so, oh, there it does it again. All right, so let's go ahead to part B. So part B says, find the displacement. Displacement is the easiest of them all in some sense because you just integrate on the interval. So our displacement is the integral on the interval 0 to 3, and we're just going to integrate our velocity function. So we end up with t cubed. We use the power rule, so we get t squared over 2. That's going to give us a 3t squared here from 0 to 3. And that will be 27 minus 3 times, oh, 27 minus 27. So that's 0. So our displacement is 0. Displacement is 0. All right. And then part C says find the distance traveled. So distance traveled, we are going to integrate, and there's a shortcut here. There is a shortcut, and if the displacement is 0, is it obvious that this area here must match that area? If the displacement is 0, that means we moved in the negative direction the same distance as we moved in the positive direction. So what we could do, there's going to be 3 ways that we could find the distance traveled. So the distance traveled, we know that this distance here, that's above the t-axis. So if we integrate from 2 to 3, that's going to give us a positive number, correct? And then what would we do to get the distance traveled? Could we modify that in some way?
You times it by 2.
Bingo. Times that by 2, that will work. So let's just, for grins, notice that we could also do this in another way. We could also say the distance is, if I integrate from 0 to 2, the function, the velocity function, what kind of number is that going to give us?
Negative.
A negative. So instead of multiplying by 2, we're going to multiply by
-2.
-2. Yeah. So that's another way. And just for grins, let's do one more. I don't know where this 2 was coming from. I don't know where that 2 came from. Okay. And a third way, let's just say that, or we could also go 2 times the integral. If we switch the order of the limits of integration, doesn't that just multiply a -1? Or if you switch the order of integration, if you switch the limits of integration, that has the effect of multiplying by -1. If you integrate from 0 to 5 and get an answer of 7, if you then switch it and integrate from 5 to 0, you're going to get a -7. So if you switch the order, so we could also do that. We could still focus on the 0 to 2 interval, but we could swap the limits of integration. So then this is now going to be positive and then double it. So it doesn't matter which one of these we do. I'm just going to do this one right here for the heck of it, -2. We're going to integrate, and we have this antiderivative from 0 to 2. So plugging in 0 is going to give nothing. So we just really need to focus on the upper limit. So that's going to be 8 minus 12. So we'll end up with 8. And I don't know, I don't think they gave us distance on this one either. So, oh no, they gave us meters per second. Okay, so let's definitely put some units in here then. So we are going to have 0 meters displacement. We are going to have 8 meters distance traveled.
Hey, Jim.
Yes.
Is there also a way to like use absolute values around those?
So that's a great question, because you've seen that the definition for distance is the integral of the absolute value, but we don't have a mathematical way to integrate this. Right? You can't integrate an absolute value unless you break it apart into its 2 pieces. Because remember that an absolute value is a piecewise defined function. An absolute value is...
So can we break it apart from 0 to 2 and then 2 to 3?
Yep,
Yeah.
absolutely. So that's how we would do it. If we wanted to do it with the concept of absolute value, we would integrate from 0 to 2 and multiply by -1, and then add the integral from 2 to 3. So, oh gosh, so that's what the effect of using the absolute value would do, because the absolute value is a piecewise defined function. And that's what we do. We would take the part where it's negative and multiply by -1, and the part where it's positive and keep it. So, and that's all based on this definition of absolute value. So this is the definition for an absolute value function. So yeah, we would have to figure out the transition point, multiply the negative part by -1, and keep the positive part.
I have a question.
Yeah, go for it.
Why did we multiply it by -2? Like, where did that come from?
So when we integrate, so what we said was that the displacement is 0. And if the displacement is 0, that means that these two areas must be equal.
Oh,
So that's the same area because the displacement is 0. So we're using that fact that the displacement happens to be 0. So it's kind of giving us a little bit more insight into how those two areas are related. So in other words, the total area is either this area times 2 or this area times 2. Does that make sense?
yeah, it makes sense.
Yeah. So the 2 is coming because we happen to know, because the displacement is 0, that the two areas must be equal.
So we can only do that method of where we have the -2 only when both of those two, the displacement equals 0.
Yes, that's right. That's
Okay.
right. So if this displacement was not 0, then we would do what was suggested a minute ago. We would find this area, which is the definite integral from 0 to 2 times -1,
Mhm.
and then add the definite integral from 2 to 3.
Okay, that makes sense.
Yep, that's right. So let's take a peek at this one. So this one is an exponential function. So let's take a quick peek at the graph. And when we plug in t equals 0, we see that e to the 0 is 1, 50 times 1 is 50. So we're up here at 50 when t is 0. Now, this exponential function is a decay function because on our because we have this negative here. And so on our interval, we know that this function is decaying. Will it ever reach the t-axis? Will that curve ever touch down to the t-axis?
No,
Nope, because it's exponential decay, but it never goes negative, right? It actually has the t-axis as a horizontal asymptote. Exponential decay that's not shifted up or down is going to zip into the t-axis or the x-axis, but never touch it. So what do we think about the connection between displacement and distance in this case?
They should be the same.
They should be the same, right? They will be the same because there is no movement in the negative direction, right? This velocity is always positive. And if the velocity is always positive, that means the motion is always to the right. So we can cut to the chase. So we can say that the displacement will equal the distance traveled. And that will equal the integral from 0 to 4 of 50 e to the -2t dt. Okay. All right, so this brings us to the most important integration technique that you learned at the end of Calculus 1. What integration technique is that?
U substitution.
U substitution. Excellent. So typically with U sub, you're going to let U be an exponent, an angle, what's inside a square root, all those types of things. And then we have to figure out the relationship between dt and du. So you can think of it in two ways. You take the differential of each side, you take the derivative of each side. There's few ways to think about that. And if you're not feeling comfortable with that, tell me and I'll try to explain it to you. Does that make sense to everybody, that next step there? Anyone befuddled at all?
Yeah, makes sense.
Do we have to write out the let u equal this for all x, or can we just use that?
You can just write it just the way I wrote it. Yeah.
Okay,
Yeah.
awesome.
Yeah. You don't need to write. Yeah. You don't have to do that. We'll focus just on the essentials here. And then what I want to do is isolate the dt. That's, I think, the easiest way to see how to substitute it back in. There are some fancy things. You could take the 50 and write it as 25 times 2 and then move the 2 over so it's next to the dt and try to do it that way. Generally, it's just simplest if you isolate the differential here and then pop it back in. Usually the easiest thing. Now that 50 can pop out to the front, and then we're going to have e to the u, and the dt right there, that's getting replaced with du over -2. -2 is a constant, so it can float right to the front. And now we have to focus on our limits of integration. So this equation right here, that relates u and t. And right here, these limits of integration are t limits. And so we're going to want to convert those over to u limits. And so we think to ourselves, okay, if I plug 0 in for that t and simplify, we get that u is 0. If we plug in t equals 4 right there, we get that u is equal to -8. So now we've converted our limits. Now we can integrate, and we know the exponential function, coolest function of them all, it is its own derivative, it is its own integral. So that'll be e to the u, 0 to -8. Now, if we wanted, let me just point out, if we wanted, we're integrating 0 to -8, so it's kind of weird. We're integrating to the left, right? We're starting at 0 and then going over to -8. Usually we like to integrate from left to right. It doesn't matter, but you could do this just as if you wanted to. You could say, you could switch those limits of integration. And if you switch the limits of integration, you multiply the front by -1 to get rid of that. Could do that. Yeah. Does that make sense?
I'm just a little confused again. Back to how'd you get -8 and 0?
So this statement right here connects t and u. So these limits of integration right here, those limits of integration are t. Those are t values. So when t is 0, we plug in 0 right here to figure out what the corresponding u value is. So plugging in t equals 0, -2 times 0 is 0. So that's why the corresponding value for u, these are u values, is 0. Plug in the +4 for that t, 4 times -2 is -8. So the corresponding u value would be a -8.
Okay, got it. Thank you.
That makes sense? Okay. All right, so now let's go ahead and evaluate this. We are going to plug in our upper limit. So that's e to the 0 minus e to the -8. We know that e to the 0 is 1. And that is our final answer. And was this the one where they said we were dealing with meters? Yep. And so now that is our answer in terms of meters right there. So that is both the distance traveled and the displacement.
If
Now-
this was on an exam, would you want us to simplify the answer? Could we just leave it like that?
You could leave it like that. I mean, there's not real, the only thing that might classify as simplify is get rid of that negative exponent. Is that what you're thinking?
Yeah.
Yeah, it's totally fine to leave a negative exponent. I mean, a lot of times we will rewrite with, if it's convenient to rewrite something without a negative exponent and it sort of makes the answer look nicer, we sometimes do it, but in this case, it looks worse. But you could go down this whole thing and, get a common denominator and do this. And there's really no rule for this kind of thing, because some people might say, hey, that looks more simple than this looks. You know, it's kind of 6 of one, half dozen of the other. So usually when we say simplified, usually we mean clearing out fractions for sure, simplifying any square roots for sure, eliminating negative exponents if it adds value, if it somehow makes the answer more useful in terms of finding zeros or something. But this is totally fine. All right, so here I want you to notice something. I want you to notice something.
Can I ask a question real quick?
Of course.
So on the line, just one up above the answer, where you
Right
have
here?
negative 25. Yep. So, why is the -8 up on the top on the left side, and then it's down on the bottom on the right side?
So let me just write what I did in general over here. If you have the integral from a to b of some function, and let's just say a dt, this will be -1 times the integral from b to a of the function dt. So if you switch the limits of integration, so notice that I switched these.
Right. Okay. I missed the negative sign there.
Yeah.
That
Yeah.
makes sense.
Yeah, no problem. So it's just a sort of clever way to get rid of a minus if you have a minus in front. So here's what I want you to notice. So somebody tell me this. If you have a function, let's suppose you have f of x equals e to the 3x. Can you tell me what its derivative is?
3e to the 3x.
Perfect. 3e to the 3x. So what you did was use the chain rule, and the chain rule said, you know, the derivative of an exponential is itself multiplied by the derivative of the exponent. Now let's look at a related problem. What if we integrated e to the 3x? Now let's focus up here for a moment. Notice we have an e to the -2t here. What did we end up doing? We ended up dividing by -2. Very similar to the chain rule. If you were taking the derivative of this, you would have multiplied by -2. But notice that when we take the integral, the effect of this substitution was that all we did was divide by -2. And this is going to be a pattern that will persist. And we are going to refer to this as the reverse chain rule. And we are going to do this a lot. And what the reverse chain rule does is it gives us a shortcut to find the integral when you have a linear substitution. When you have a linear u sub, you don't need to do u sub. You can save these 3 steps. It's actually more than 3 steps if you have a definite integral, because then we had to convert the limits also. You can save time, and we are going to probably see, you know, 500 versions of u sub this semester. And if you're adding in, say, 3 or 4 extra steps just because for the u sub, that's a lot of steps that you can bypass. Get back where I want you, right there. You can save a lot of steps when we have a linear substitution. If we have a linear substitution, you can just do this reverse chain rule, which means divide instead of multiply. We'll do this a lot. We'll do more examples of it. But so this is just a heads up. But we will do more examples of that. But I just want to point it out because it's right there. All right. So another one here. Here we're starting with velocity, and they're saying find the position function using 2 different techniques. So this is what I was referring to before, where there is the future value method, which they call step B, the fundamental theorem of calculus, I think future value is another way to think of it. And then using the antiderivative method. So let's do both methods. Again, I prefer this method in B because it's more general. It's what you would see in an econ class. It's what you would see in an advanced biology class. Usually they'll do it with a future value instead of the antiderivative method. But let me show you the antiderivative method first. This is a method you probably have done already. So our goal is to find the position from velocity. So we know that position is the integral of velocity. So in this context, we are going to use an indefinite integral. And we know that an indefinite integral is going to have a constant of integration. So we have partially found the position function by integrating, finding an antiderivative. But then what we have to do is use this initial position and resolve the constant. So this initial position says when t is equal to 0, s is equal to 1. So s is 1 when t is 0. So that's the equation that we are going to solve to find the constant of integration. All right, so then cosine of 0, go over to 0 radians, cosine of 0 is positive 1. So C will be 2. And our conclusion then is that therefore, these little dots, triple dot triangle thing means therefore. So therefore, our function of t, our position function is minus cosine of t plus 2. That is our position function. So that's using the so-called antiderivative method. So that antiderivative method integrates with an indefinite integral and then resolves a constant. So a little bit of back and forth, you get the general kind of look of the position, but you have to resolve the constant. So you go with your initial value, plug it in, then you back substitute. A little bit of back and forth to get to the answer. Totally fine though. And I don't care which way you do it on an exam, but this way would be my preferred method. So the preferred method, S of t, so this is using the future value technique, or what they're referring to as the fundamental theorem of calculus technique.
What do those 3 dots represent?
So those 3 dots just mean therefore. So when you see that stack of 3 dots, it means therefore. And that's a lot of times in math, what we'll do is do that right when we get to an answer. We'll say, so therefore the answer is this. So here is the other method. This method is, again, I would call it the future value method. They call it the fundamental theorem of calculus method. So we use this formula. We say that the future position, the position at time t somewhere off in the future, that is going to be the initial position where we start, where the particle starts, plus the displacement on the interval from 0 to t. And then we're going to integrate velocity. But we can't use a t for the dummy variable because t is already being used. So we pick another letter. Favorite math letter is generally x, simple x. You could use whatever letter you want. You can use Greek letters if you want. You can use whatever. Doesn't matter, because that's just a dummy variable. It's going to go away. So this is the future value method. And let's just fill in the blanks. So S of 0 is 1. And then we integrate from 0 to t. The velocity function is given as sine t, but we want to use an x because we already have a meaning for t. T is going to be the variable that we end up with, right? We have this this independent variable that is going to be in the final answer. So we've already used t, so we use a different letter for our dummy variable. And so then this will be 1 plus the integral of sine is minus cosine. That goes from 0 to t. Plug in the t, and then plug in the 0. And we end up with, of course, the same answer as we had before. So this is the future position. Any questions? So the future position technique is much cleaner. You just sort of go in a straight line all the way through. But it's a little bit more conceptual because you have to remember you can't use a t, you have to use an x for your dummy variable. So a little bit more abstract, but a little bit more direct. But either method works fine. I recommend getting to know both methods, and but you can use the antiderivative method for sure. All right, let's try another one here. This one is going to have a little bit of that reverse chain rule going on. So notice in here, foreshadow, that is a linear expression. Pi times t is a linear function. So if we were going to do u sub, we would be doing a u sub that is linear, which means we could cut to the chase by doing the reverse chain rule instead of the chain rule, which means divide by the derivative of the angle instead of multiplying by the derivative of the angle. Let's see where this goes. So I'm going to use the future value method. So S of t will be the initial position plus the displacement on the time interval 0 to t. And we're going to integrate the velocity function. Well, the velocity function is given as 3 sine pi t. Oops, can't use a t. Put in an x. So that is the future position. That's the position at time t, where t is some time value in the future. All right, so now we know what S of 0 is. That's given to us. That's 1 plus, now here we go. So integral of the function, sine is the function, integral of sine is minus cosine. So we're going to have minus 3 cosine, same angle, angle doesn't change. Here's where the reverse chain rule comes into play. So if we were differentiating, we would end up multiplying by pi, because the derivative of this angle in here, the derivative of this angle is pi. So if we were differentiating, we would end up with 3 cosine of pi t times pi. But we are integrating a linear angle. So instead of multiplying by the pi, we divide by the pi. So we can divide the whole thing by the pi, just the 3 by the pi, whatever floats your boat. There we go. So that is reverse chain rule. And I think I'll rewrite it like this. I'll put the pi, I'll mash the constants together. Now I'm plugging in the upper limit first. And then we subtract off the antiderivative at the lower limit. Notice that this antiderivative is in fact negative. So when we subtract off a negative, it becomes positive. So we'll get plus 3 over pi cosine of 0. So this quantity in here, this is the antiderivative, right? So we plug in positive t first and we get this, and then we subtract off the antiderivative at the lower limit. And when we subtract off that antiderivative, we get plus 3 over pi, plug in the 0. And now let's simplify. Cosine of 0 is 1. And I'll just move that constant to the front just to sort of group it with the other constant. Do you have to? No, you don't have to. So there is our position function. So that will be S of t. So therefore S of t is equal to that.
So in these questions, like stating that t is between or equal to 0 and 4, is that not really relevant for what we're calculating here?
So great question. If they asked, so this just says determine the position in both of these. So this technically would be for t values that satisfy that interval. So technically the t has got to be somewhere between 0 and 4. So if we think about starting at t equals 0, this is predicting where we'll be when t is somewhere between 0 and 4. So that's kind of extraneous information here, because if this was not even here, we would have the same answer. And so them giving us that 0 to 4 interval, like if I gave you that interval 0 to 4, I would ask some other questions. I would say, what is the displacement on that interval? What is the distance traveled on that interval? Like, it's kind of funny that they gave us that interval at all, actually, because of what you just said.
But just whenever I see that, I'm thinking definite integral right away.
Absolutely. And I would think that way also. It's just that they don't ask us. So it just says, consider an object on this line with the given velocity and initial position. Determine the position when t is greater than or equal to 0. So they don't say anything about displacement or distance traveled, which is what we would get if we integrated 0 to 4. That would give us our displacement on that interval.
Okay, that makes sense.
Yeah,
Thank you.
so they're going to do this from time to time, throw in some extraneous information to try to psych you out. Hannah, dividing by pi is reverse chain rule. So let me come down here and do one other example, because I don't think the next page has a reverse chain rule. Let me
Can I
see.
ask a question on this one real quick?
Yeah, go for it.
So you see where it says like 1 minus above like the answer? So you know how when we were doing displacement, we always did like the t, which is the top of the, it's on the top, so it would be minus the bottom one. How come we're adding on all of these? Is it because we're not, it's like, I know this isn't displacement, it's like position. Is it because it's position that we added?
No.
Or is there
No,
like a
it's-
variable I'm just skipping on?
Yeah, this thing I'll turn to red, so I like that better in red. Okay, so this is the antiderivative right here. Do you agree with that?
Yeah.
So that's the antiderivative. And so what the rule, what the fundamental theorem of calculus says is plug in the upper limit into this antiderivative. So we're plugging in t into that, and that's why we get this right here. Do you agree with that?
Yep.
And then the fundamental theorem of calculus says, now subtract off the same antiderivative evaluated at the lower limit. And when you subtract off a negative, you see it?
Yeah, yeah.
Okay.
Thank you.
Yeah, you're welcome. Why is it doing that? Okay, so, all right. And so Hannah, this division by pi is because we're integrating and not differentiating. If we were differentiating this, let me just draw it over here. So if we had y equals, let's just forget about the 3 out in front. Let's just suppose we had this, and I'll put an x instead of a t, doesn't matter. So if we were differentiating, do you agree that this is the answer that you would get? And then if we're integrating, same function, the integral of sine is minus cosine, so it's minus cosine of pi x, but then instead of multiplying by pi, we divide by pi, so I'll put it as a 1 over pi out in front. So integrating, we divide, differentiating, we multiply. And we'll do another example that will have that in it shortly. Okay, so cool. All right, so this is kind of a summary. Here is the future value method. So this is what I'm going to refer to as the future value method. Or they call it the fundamental theorem of calculus method, future value method, fundamental theorem of calculus method. And down here, all they do is generalize it to other, instead of just focusing on position or velocity or acceleration, This generalizes it to any sort of function. So the function could represent population or something like that. So here is future value method where we're going to find velocity from acceleration. And then down here, future value, if you had a population of whatever, bacteria, animals, we're going to use a Q instead of a V or an A or an S. So that's just the kind of general form of this future value method. So let's go ahead and do a couple more examples. So let's do one where we find position from acceleration. So we know that if we start it with acceleration, we have to integrate 2 times in order to get up to position. You integrate acceleration once and you get velocity, integrate velocity and you get to position. So let's do it. So we're starting with, obviously we're talking about negative 32 feet per second squared. They don't tell us that, they don't give us units, but we know this is what they're sort of implying. The acceleration due to gravity near the surface of the earth. Okay, so first we're going to find velocity from acceleration. So velocity will be the initial velocity plus the change in velocity on the time interval. And the change in velocity is the integral of acceleration. And then we can't use a t, so we use an x. So that is our future velocity given our initial velocity and the change in velocity. V naught is 50. And then we integrate negative 32 and we get negative 32x from 0 to t. And if we plug in 0, we get nothing. So we only are going to end up with this. So this is our velocity function. That's our velocity at time t. And typically we think of t as representing time. So that tells us. Plug in 0 and we get 50. Plug in 1 and the velocity is 18, theoretically, feet per second. That makes sense? So this
So
is,
when you're using this method, you don't have to do the thing with the constant and then plugging in. Okay.
that's right. Do you pronounce your name Eliana?
Yes, Eliana.
Okay, thank you. Yes, so that's correct, Eliana. So when we are using that other method, the antiderivative method, we use an indefinite integral instead of a definite integral, but then you get the plus c and you have to find the c and plug it back in. With the future value method, we can just do it directly. So we use a definite integral from 0 to t with a dummy variable of x, and the initial value is right here in front. So I like this method better just because it's a little cleaner, it's more direct, and you're not doing that sort of back substitution thing. But of course it will work. Either method will work. So now let's keep going. Now we have velocity. Now we can find position from velocity. So position at some future time t depends on where you start. You need your initial position, but then you're going to add 0 to t. And now we're going to put our velocity function in here. But again, can't use a t. We already have t spoken for right there. Now we plug in our initial value. So s of 0, ooh, it's 0. Okay. And then we integrate this with respect to x. And there's 0 to t. Now we plug in our upper limit of integration. Plugging in the upper limit of integration gives us this. And then we subtract off the antiderivative at the lower limit of integration. Lower limit is 0. Plug it in, we get 0. So that we are done. Here is our s. There is our v. So we've got our velocity function, and we now have our position function as well. Oh, good.
I have a quick question.
Yeah, go for it.
So in the answer for the V, you said when we're like evaluating and plugging in the 0, wouldn't it be like negative 32 and then you plug in the 0, that's 0, but wouldn't you still have the 50 left? Or
So I think I'm understanding your question. is it clear that this is the antiderivative right here? We're not using the 50 twice, if I'm understanding you, right? So this 50 is out in front. It's sitting in front. And this is the antiderivative that we're plugging the 0 into and the t into.
Oh, so the 50 it just stays. I see. Never
Yeah,
mind.
so the 50 is disconnected from the antiderivative. It's 50 plus the antiderivative. And the antiderivative is negative 32x. So we're not plugging t into this whole thing.
Hmm.
And then 0 into this whole thing where you would get the 50 minus 50 and they'd cancel.
Yeah, that's what I was thinking. Okay, that clarifies it.
Yeah, so the 50 is not part of the antiderivative.
Okay.
So fundamental theorem of calculus is telling us plug in the t, plug in the 0 into the antiderivative.
Mhm.
And so this 50 is out in front. It's not part of the antiderivative.
Okay.
All right, let's do one more of these. So same method. So we're going to find our velocity by taking the initial velocity and adding the change in velocity on the time interval 0 to t. And so in here, we're going to put our acceleration. Oops, I almost put a t. We already used t, so we're going to use an x. And then v of 0 is 60. All right, here is another reverse chain rule. You could use u substitution, du is equal to minus x, u is equal to minus x, so du is minus dx, absolutely. But this is a linear substitution, and when we have linear substitutions in this class, we are going to reverse chain rule. So linear substitution up there. So we know that the integral of an exponential is itself. If we were differentiating, we would multiply by -1. We are integrating, so we're going to divide by -1. Same in this case. And then that goes 0 to t. So we will end up with 60 minus e to the minus t. And now when we, and so once again, kind of like that last one, this is the antiderivative right there, right? That's the antiderivative. That's what we're plugging our t and 0 into, the 60s out in front. So, but now we subtract off the antiderivative at the lower limit. So again, we're subtracting a negative. So we are going to get a positive, subtracting a negative. And we have an e to the 0. And this becomes 61 minus e to the minus t. So there is our velocity at time t. Because e to the 0 is 1. Now we can find position. When I scroll down. Why did it just change the color of that? Bah, humbug. Okay, so now we're going to do the same thing, but we're going to find position from velocity. So let's come down here. We're going to say position at time t will be the starting position plus the change in position. And to find the change in position, we integrate our velocity function. Well, there's our velocity function. The one modification, change the t to an x because we already have t being used as a limit of integration. And I need to bounce up here to see what was s of 0. S of 0 is 40. Okay, now let's integrate with respect to x. So we're integrating 61 with respect to x. And now we're going to integrate e to the minus x. So we've got this minus that just drops in, right? This minus is a constant, so it just comes down. Now we're integrating this part. The integral of an exponential is itself, but then we have to divide by the derivative of the exponent. The derivative of the exponent is -1, so we divide by -1. I'm going to write that here just to emphasize. Obviously, the 2 minuses will just turn into a plus in a moment. And then we go 0 to t. And here's what was brought up earlier, a little bit of it can look a little ambiguous, right? You might look and say, hey, isn't this whole thing the antiderivative? Shouldn't the t and the 0 be plugged into that whole thing? And of course, the answer is no. We've talked about it a couple times already. Whoops. It is not, the 40 is not included in the antiderivative, right? The antiderivative is just this part. So that's where we're plugging our 40, excuse me, our t and our 0 into. The 40 is free and clear. Okay, so plug in the t. We get 61t, and a minus and a minus is a plus, e to the negative t. But now we have to subtract off antiderivative at 0. So subtract off antiderivative at 0. Well, when we plug in 0 here, of course, that's 0. But when we subtract off this part evaluated at 0, we're going to get a minus because we're subtracting off a positive. And e to the 0 is 1. So we will end up with 39 plus 61 times t plus e to the minus t. So that will be our position function. All right. One more example in this section. Let's do one that is a generalization. So instead of S, V, and A, let's go with foxes. Let's go with a population. So this tells us some information about the foxes, tells us the rate at which the population is changing. So this is empirical. We can go out there and physically measure P prime. We can build that function by looking at data, right? So we can build that function very easily. And this is very common in math and science where you can empirically come up with a rate of change, a population, an amount like a radioactive substance, whatever it is. It's very easy to figure out the rate at which something is changing. And in math and science, what we want to do is to use that to predict future value. That's a very common strategy. So we're looking at this population of foxes that start with 35. We know the rate at which they're changing. And so let's figure out, well, how many foxes are there going to be in 15 years, 35 years? Let's check. All right. So now one thing, this is backwards here, right? We know that if we have our P of t function, we would plug in 15 for the t and then 35 for the t. The more kind of correct way to do this would be, let's just find P of t and then plug in the 15 and 35. That makes sense? So they have this kind of lined up a little backwards, in my opinion. Okay, so the future value of foxes, the future population, will be the initial population plus the change in the population on the time interval. And the change in population is found by integrating the derivative. So that's our generalization. That's what we just have been doing for the last hour. All right, let's plug and chug. So P of 0 is 35 plus integral 0 to t of 5 plus 10 sine. And I'm going to write this angle as pi over 5 times t, just to make it times x dx, just to make it a little more obvious what the coefficient of x is, because that's that makes the linear, that's a linear substitution. Okay, so that gives us 35. So that's not part of the antiderivative. Now we're first going to integrate 5 with respect to x. And now we're going to integrate sine. Integral of sine is minus cosine. So we're going to have minus 10 cosine. This angle does not change when we integrate. But we have reverse chain rule. When we look inside here, the derivative of the angle is this right here, right? That is the derivative of the angle. This is a linear substitution if we were going to do u sub. So what are we going to do with that pi over 5?
Divide it.
Divide it. So we're gonna divide by pi over 5. And then this goes 0 to t. And first we're gonna plug in again, antiderivative. So the 35 is out in front, not part of the antiderivative. So first we're gonna plug in t into this whole thing. So we will get 5t. Let's simplify these constants. 10 divided by pi over 5, we multiply by the reciprocal, so we get 50 over pi. Cosine pi over 5 times t. Now we're subtracting off the antiderivative at 0. So the antiderivative is this part. Plug in 0 here, you get 0. But now we're subtracting a negative, so this will be positive, and we plug in 0. Cosine of 0 is 1. So we end up adding 50 over pi. And there's no like terms or anything here, so this is our future value function. This tells us the population of foxes at some future value of t. And we wanted p of 15 and p of 35. Plug in 15, we're going to get 35 plus plug in 15 there. That's 50 plus 25, that's 75. Minus 50 over pi. What is cosine of 3 pi?
-1.
So cosine of 3 pi. So remember your unit circle. You want to have those down pat. So with the unit circle, we're thinking of our unit circle. 1 pi is right there. 2 pi is right there. 3 pi pops us right over to there. Cosine is the x value. The x value at that point is -1. Good. So our p of 15 is going to be, what's 35 plus 75? That's 110. So we'll get 110 minus 50 over pi. And you just told me that was -1, so that makes a plus. Oh, and we have a 50 over pi plus 50 over pi. That's 100 over pi. And if we wanted to, we type it into our calculator, approximate it to the nearest fox, and we'd be golden. All right. So the last slide in this section is just a summary of what we just did. And on Monday, I will see you in person at the Westminster campus. And I think we're in B1204. Anyone that has questions about the technology and stuff, I know a few of you were having a little Teams issue, little OneNote issue. Stick around. Those of you that are good to go, I will see you on Monday. Have a great weekend and do some math. Take a look at 6.2 and 6.3. We will be covering those we'll do 6.2 and most of 6.3 on Monday.
Okay. Thank you so much, Professor.
Thank you.
Absolutely.
Thank you.
Thank you.
Thanks.
Thank you.
And
Thanks
Yeah,
for
everyone.
Zooming with me.
how do you like to be addressed, by the way?
Oh, you can call me Jim. You can call me Mr. Voss. You can call me Professor Voss. Doesn't matter.
Well, thank you for the lecture, Jim, and I will catch you next week.
All right. See you on Monday, Dan.
So is there anything we need to do by Monday?